So let's see an example of these Cauchy-Riemann conditions in action. Okay, it's a simple example. F of z equals, show that f of z equals z squared is analytic. So to show this, it's analytic if and only if the derivative exists, and we then, for every point and a neighborhood surrounding that point. A proper way to show it's analytic, if we don't know anything else, is to actually show that it obeys the Cauchy-Riemann conditions. Okay, so the Cauchy-Riemann conditions require us to represent this f of z equals z squared as a real part and an imaginary part involving functions of x and y. So we write z equals x plus iy, square it, and we get, well, obviously x squared minus y squared, because we got y squared gives us a minus sign, and the cross product gives us 2i xy. So that means that u of xy is x squared minus y squared, and v of xy is 2 times xy. So applying the Cauchy-Riemann conditions, we want to check if they're satisfied. So we've got u was x squared minus y squared, so du by dx is 2x, and v was 2xy, and we're differentiating 2xy with respect to y, we get 2x as well, so that's tick, that's always true. And the other one is, the other condition is du by dy, so u, remember, was x squared minus y squared, so when we do du by dy we get minus 2y, and sure enough that's equal to minus dv by dx, because v was 2xy, differentiating with respect to x we get minus, 2y, and there's a minus sign, so we get minus 2y equals minus 2y. So those conditions are always satisfied. So that means that z squared is analytic everywhere. And if we want, we can also work out the derivative. So the derivative we can find from either du by dx plus I dv by dx. So remember, du by dx is 2x, and dv by dx was 2y. So sure enough, we get 2x plus I dv by dx, so plus 2iy, and that's, if we replace x plus iy by z, we get 2z. As you would sort of expect, you would sort of guess that the derivative of z squared should be 2z. You would hope that. Right, next example. We could show it another way. So it should be equal to this. Well, okay, it's obvious it's equal to this because these gives us the Cauchy-Riemann. We don't need to show that again. Okay, next example. Show that e to the z is analytic. Okay, so again, we do the same sort of thing. We write z as x plus iy. Then we can split that as e to the x times cos y, and, well, e to the x obviously is real all the time, so e to the iy is cos y plus I sine y. So we split into real and imaginary parts. This is u, and this is v. So again, same thing, we do du by dx, and we get e to the x cos y, and we do dv by dy, and we get the same thing, because differentiate sine y, we get cos y. So e to the x cos y, we get the same thing. And du by dy gives us minus e to the x sine y, and similarly dv v by the x minus gives us e to the x sine y with an extra minus sign. So the Cauchy-Riemann equations, again, also always work. And the derivative we get by adding du by dx, which was e to the x cos y, to I times dv by dx. Sorry, I times dv by dx, which is yes, just the same thing. So the derivative is indeed e to the x times cos I plus I sine y, which is indeed just the same thing. So the derivative of e to the z is still e to the z. Right, so final example, let's look at something which is not analytic. So the function f of z equals mod z squared is not an analytic function. Well, why? Easy to see. If we work out what this is in terms of real and imaginary parts, well, the modulus of z squared is of course x squared plus y squared. So we've got u equals this and v equals 0. So obviously when dv by dx, if we do du by dx, then we get 2x. dv by dy is 0. So we only get the Cauchy-Riemann equations being satisfied if x equals y equals 0. The other one obviously is going to give you 2y equals 0 again, which is only true if y equals x and y are 0. Now the problem is, you might say, oh, does that mean that this is analytic just at that single point? But there's no such thing as a function which is analytic at a single point, because to be analytic, it needs to be well behaved in an open set. So there needs to be points outside that point where it's also analytic. Also, the derivative also exists. So actually, mod z squared is not analytic anywhere for that reason. Okay, so you can now do question 12. Show that any branch of log z is analytic and find its derivative. So, do we need the Cauchy-Riemann equations every time to show that a function is analytic? Well, fortunately, no. So we can actually use the normal rules of differentiation, normal formula for differentiation of real functions also apply when you differentiate complex variables. So basically it means that if f and g are analytic in some domain D, then automatically f plus g, f times g, f of g are also analytic in that domain. F divided by g is analytic as long as g is not 0 in that region. So for example, if you want to show that sine z is analytic, all you need to do is say, well, sine z can be written in this way, but I've also already shown that e to the z is analytic. Z is analytic, e to the z is analytic, I times z is analytic, so e to the iz must be analytic. So this is a difference of two analytic functions. That means it is itself analytic. So sine z is analytic everywhere, except possibly at infinity. Okay, so now you can do question 13 as well. Show that f of z equals z star is not analytic, and hence argue that these functions, real and imaginary part of z, are also not analytic functions.